And in today's lesson we are going to talk about ideal and non-ideal solutions. We studied the routes law, we saw the application of the routes law, we did the boiling point and the vapor pressure composition curves, and we saw the concept of fractional distillation. We saw all that. So today we are going to talk about the non-ideal solutions, or real solutions, or imperfect solutions. Remember, with ideal solutions, these ones, they are ideal. They obey to the route law, whereby it is assumed if you get the mole fraction, multiply it with the partial vapor pressures of these two gases, you get the vapor pressure of the solution mixture. It is assumed that each gas or each solution, each component contributes independent of each other. So those are ideal solutions. But now with non-ideal, now these ones, they don't obey to the route law. In that way, you're assuming if you use the route law to obtain the vapor pressure of the solution mixture at a given composition, now these ones, they either go above the route law or they will deviate negatively from the route law. Okay? So those are the two deviations that we shall find. Okay? And actually those are the real solutions. It's hard to find an ideal solution. So real solutions is the one which show deviations from the ideal behavior, from the route law. If the route law predicts this, if you remember, if the route law predicts this, let me do this. So if the route law predicts this, that the vapor pressure of this composition is going to vary like this, then these real solutions, they will either deviate negatively, the vapor pressure will always be above that is predicted by the route law, or they will be below that predicted by the route law. So I hope if I say route law, we all know what route law is. So they arise from differences in the intermolecular forces of attraction, the adhesive and the cohesive forces, or between the like molecules and unlike molecules. For instance, you can have a look. With the route law, it's like this. If you have solution mixture A, okay, if you have A and B, and these two are mixed to form a solution mixture, for them to obey the route law, the intermolecular forces of attraction holding A molecules together should be equal or equivalent to the intermolecular forces of attraction holding the molecules together. Okay? So that the new forces of attraction that will hold Ba molecules, they will be equal to these cohesive forces, to these molecules, to these forces of attraction holding like molecules. That's when it will obey the route law. That's when it will be referred to as an ideal solution. But in real solutions, okay, in real solutions, the intermolecular forces of attraction holding like molecules, those are cohesive forces. The intermolecular forces of attraction formed between like molecules, they are either high or lower than the intermolecular forces of attraction, holding, and like molecules, the adhesive forces. Okay? Adhesive forces. So as a result, then the solution is going to behave, is going to deviate, okay? Deviate either positively or negatively from the route zone. The vapor pressure is going to either be higher or lower than the predicted vapor pressure of any solution mixture by the route zone. So that's what we call positive or negative deviation. Is that really good? Yes. So the vapor pressure of such solution is either high or less than the predicted from the route zone. So therefore it will either deviate positively or negatively. So let's talk about the negative deviation. Now the negative here, if this is the vapor pressure that is predicted by the Raoult's law, okay, this is the vapor pressure, how it is going to vary of this solution mixture that is predicted by the Raoult's law, okay, then for the negative deviation, the vapor pressure becomes lower than what is predicted by the Raoult's law. So if we consider the blue one, this one is variation. It shows variation of vapor pressure, okay, of liquid. This is mole fraction of A, this is mole fraction of B. So this is for mole fraction of A with composition. So the variation of vapor pressure with mole fraction of A. Whereas this one shows variation of vapor pressure with mole fraction of B. And this is the vapor pressure of pure B. This is the vapor pressure of pure A. Now you can all see that if this is the line that is predicted by the ideal behavior or by the Raoult's law, if you actually plot, okay, if you actually plot the real vapor pressure of this solution, if it negatively deviates, this is the vapor pressure composition curve that you will obtain. The same applies to this. If this is what is predicted by the Raoult's law, okay, then if you are to plot the real vapor pressures, if the solution deviates negatively, then this is going to be the vapor pressure composition curve, okay, with mole fraction of B. Now, if you know this vapor pressure composition curve, then can you think about the boiling point composition curve? Is it going to give a maximum boiling point or a minimum boiling point? Think about it. Is the boiling point going to be higher than expected, or it will be lower than expected? So basically, if you understand that, then you'll be good to go. So with negative deviation, it occurs when the vapor pressure of the system is lower than that expected by the Raoult's law. Okay? Yes. So if you know the partial vapor pressure, okay, of each component, for example, A, and you know the mole fraction of A, okay, you know the partial vapor pressure of B, okay, and the mole fraction of B, then from this you can get the pressure at any mole fraction by Raoult's law. Okay, now this is by Raoult's law, but when you carry it out experimentally, you find that actually the variation is going to be lower than what is expected by the route snow. So that's why it gives a negative deviation. So basically that's how simple it is. Now, why is it so? Think about it. Just think about it. With the route law, the intermolecular forces of attraction between like molecules are assumed to be equal to the intermolecular forces of attraction between unlike molecules. And so it will follow that ideality. It will deviate, it won't deviate. Okay? But now here, why is it deviating negatively? Think about it. Yes, we are thinking. Maybe let me first take off here. Think about it. Yes, that's good. That's brilliant. So now, ideally, all forces of attraction are equal between the cohesive forces and adhesive forces. They are all equal. So they will all contribute negatively. Okay? So that they will all contribute independently of each other. But now here, the forces are different. Okay? Whereby the new forces formed are stronger than the individual forces. So therefore, you deviate negatively from what you expect. You don't reach the vapor pressure that is expected. Okay? And you see, you have a look. You have M molecules, okay? M molecules. And at 20 degrees Celsius, it supplies vapor that is maybe 760 mmHg. Okay? Those are individual A molecules. Then you have B molecules, still at the same temperature 20, the B molecules maybe supplies 700 mm. That is its vapor pressure. That is the vapor above the liquid. But now, when you mix the two, maybe 50-50, instead of getting the vapor pressure that can be predicted by the route snow, you know the equation, you are getting the vapor pressure that is way below these two. Maybe you are getting 608 milligrams mmHg at the same temperature, 20 degrees Celsius. Why? 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 It means the new forces of attraction formed between A and B, they are way stronger than the individual forces of attraction between AA molecules and BB molecules. So that you need relatively higher amount of heat to break these forces of attraction. So that at the same temperature, 20, 20, 20, it will be hard to overcome these forces of attraction so that molecules of AB escape to the vapor phase. So as a result, the vapor pressure is going to be slightly below what is expected by the route snow. I hope it is okay. If it's not, guys, feel free to ask. So it leads to the reduction in the escaping tendency, to the rate at which molecules escape to the vapor phase. Okay? Because they are strong, the new forces of attraction between the unlike molecules, the new adhesive forces of attraction are stronger than the individual forces of attraction between unlike molecules. So you reduce the escaping tendency to the vapor phase so that you reduce the vapor pressure at 20 degrees Celsius. And so it will deviate negatively throughout. And so, I hope it is really good. Now, if you are to sketch the boiling point that shows the negative deviation, can you think about it? Just think about it. Let me give you 1 minute. 1 minute, it is counting 38, 39, 40, 41, 42. Yes, think about it. How is it going to vary? Yes, 54, 55, 56, 57. Yes. So now, the boiling point is going to give a maximum. Okay? Why? Because the mixture will have a low vapor pressure, and so the boiling point is going to be high. Why? Because the rate at which the molecules would escape to the vapor pressure, to the vapor phase, is going to be low. So the temperature at which the vapor pressure above the mixture or above the liquid mixture is going to be equivalent to the atmospheric pressure is going to be achieved at a high temperature. That one is achieved at a high temperature, which accounts for a high boiling point. So therefore, the boiling point composition curve is going to be like this. Can have a look? Yes, it is going to be maximum. Okay? Yes. Whereby this is the boiling point of the pure liquid mixture. No, of the pure liquid. Maybe it is A, pure A. And this one is the boiling point of pure B. Okay? So you can see pure A is at slightly lower boiling point than. So the B is at slightly lower boiling point than A. So this is the liquid phase, this is the vapor phase, and this is the liquid vapor equilibrium. But now, whereas the other one, we were able to fractionally distillate and successfully separated the two components by fractional distillation. In this case, where we have deviation, yes, you successfully separate one component, and then the other component won't be able to be isolated. That if you fractionally distillate, you will finally form a liquid mixture with a constant boiling point that gives off a vapor with a constant composition, that even when you cool down the vapor, it will give a liquid mixture with a constant composition. And that liquid mixture is called an azeotrope. An azeotrope, it's a liquid mixture with a constant boiling point. When heated, gives off a vapor with constant composition, and when the vapor is cooled, it gives a liquid mixture with constant, and actually the same as it was before the heating. Not so? We call it an azeotrope. And that liquid mixture is this. Okay? Yes. So you can take a look, for instance. We are heating. We are going to fractionally distillate. Okay? Our liquid mixture. Now, at this percentage composition, for instance, here. So when you fractionally distillate this, it will boil at this temperature. Okay? Giving off the vapor that is this. Okay? And then when heated, we shall get a new composition, which is this. And a distillate it will remain. Now when you keep heating the distillate, you end up forming a liquid mixture with a constant, which will be given as a residue. Okay? And this residue will be constant. Even when you heat a liquid mixture of this, you heat it and it will boil at this temperature, giving off this liquid mixture, so the vapor, and the vapor you cool, it gives this composition. You heat, okay, it gives this new vapor, and when you cool it down, it will give a liquid mixture of this composition. You heat again, so you obtain pure A. If this is A, you will obtain pure A as a distillate, and an azeotrope or an azeotropic mixture as a residue. Okay? That here you cannot further separate it using physical means by mere heating. Then you need to employ other means, okay, of separating that azeotropic mixture. Is that really okay? Is that good? Yes. I hope it's really good. So, what is an azeotrope? It's a liquid mixture that boils at constant boiling point or constant temperature, yielding vapor of the same composition as that of the liquid at constant pressure. Like how you've seen. Let's go. Let's first. If you have this is your azeotrope, and it has this percentage composition. Now, if we boil this azeotrope, if we boil this mixture, isn't it going to boil at this temperature? Even the same applies to this. Won't it boil at that temperature here and here? Yes, it will. Now, when we, how is the vapor pressure going to be? Isn't the vapor pressure almost similar to the boiling point? Yes, they are. So what does that mean? If we cool this vapor then, aren't we going to get the liquid mixture with the same composition? Aren't we? Yes, we shall. So that's what we call an azeotrope. You heat, you get a liquid mixture of the same composition, and it boils at constant boiling point. So that's what we call an azeotropic mixture. So you can have an illustration. So you can see here it is an azeotrope, and this azeotrope, it shows a positive deviation, no, a negative deviation. Now it is a positive azeotrope because its boiling point is higher than the boiling point of pure substances, but it shows negative deviation. But this one is a negative azeotrope because its boiling point is lower than the boiling point of the pure liquids, but it is formed by the positive deviation. So if there are some questions, then it's okay, it's the right to attend to them. So that is the azeotrope for you. So let's see some few different properties of an azeotropic mixture. Number one, it has a constant boiling point. Yes, even if you fractionally distillate, like how the boiling point cannot change, you have to just leave what you have extracted and then you apply other means. Then they do have the fixed composition, both the liquid phase and the vapor phase. they have a fixed composition, like how you saw. So you boil, it is heated, then it vaporizes and forms a vapor phase. Now the composition in the vapor or in the vapor phase, it will always remain the same. And the composition in the liquid phase, it will also remain the same. Not so? Then, if they are the same, if everything is the same, how shall we even separate this azeotropic mixture? We can employ different physical methods, okay? Such as, now, let's start with chemical method. And here, if the mixture is for water and ethanol, for instance, then we shall use the quicklime, which is calcium oxide. So you know this is a dehydrating agent. You know that so well. So whereby you shall get your mixture, your liquid mixture of ethanol and water, which is an azeotrope. Okay? That cannot be separated by fractional distillation. And then you just add there calcium oxide and it quenches out all the water in the liquid mixture. Okay? You quench out all the water in the liquid mixture. So what will remain is pure ethanol that does not have any water. Then we can use distillation using a third component. Okay? Now here we get an azeotropic mixture, maybe of ethanol and water, and then we add there another volatile component. Okay? This time around we use a more volatile, in fact. Now, if you add there a volatile component and you start and you heat, because you have this volatile component that is insoluble in water, it will vaporize, it will cause this solution mixture to vaporize at low temperature. Okay? So that you get the ethanol and together the other component that you've added, which is benzene, into the vapor, and then you condense, and water remains as a residue, because for it has relatively high boiling points. So the azeotropic mixture of ethanol and water can be separated by addition of benzene, which is a third component. Then distilling the mixture of the three, then you do fractional distillation of the mixture of the three components. So first distillation yields an azeotropic mixture of three components. Then the second distillation produces a mixture of ethanol and benzene on distilling the mixture. Then on distilling the mixture of benzene and ethanol, you shall form a pure ethanol solution or solvent. Then another important technique is solvent extraction, and we shall study this deeply. Here you have one component that has more affinity for the dissolved solute, and another one has less affinity. So let's take, for instance, let's say for instance you have in ethanol, in water, you have there iodine. Okay? In water. Now you cannot use fractional distillation and you remove iodine from water. So what we do, we can use solvent extraction, where we get one component or one reagent that has more affinity for iodine than how water is. and automatically that must be an organic solvent. Then you mix the solvent with this water and you shake, so that iodine being more soluble in iodine being more soluble in an organic solvent, any organic solvent, it is going to be extracted from the water. And you have pure this, you have your pure water and the pure iodine. So you can use solvent extraction, okay, by using a solvent that is more dissolving in another. Then adsorption, always effective by addition of silica gel, which absorbs one of the components. So finally, we have some question here, and it's a good one. And the question says, at constant temperature, a mixture of 11.95 grams of trichloromethane. So you have 11.95 grams of chloroform, CH3, Cl, and 14.5 grams of propane. Okay, so this is propane. No, this is propanone, not propane. So it is a ketone. It was sorry, it's a misconception, it's a tongue. So this is propanone, CH3, and then CH3. So this is propanone. Now they do deviate from Raoult's law. In other words, if you are to calculate using the Raoult's law and you obtain the pressure by Raoult's law, then these ones, when you actually experiment it, when you actually carry out, you find that they will deviate from Raoult's law. Now the question does not tell us if they do deviate positively or negatively. I think that's what they want you to show. And they are telling us that deviates from Raoult's law. And it has a total vapor pressure of 300 milligrams. So this is the pressure, okay, of the liquid mixture with this and this. Not so? Now, if the saturated vapor pressures at that very temperature of propanone and trichloromethane is this and this respectively, can't you state the type of deviation from Raoult's law and explain how? Okay, how does the mixture of trichloromethane deviate from? So this question should come before this. Okay, so you're going to determine, you're going to calculate, you're going to find how this liquid mixture deviates from Raoult's law, and then after you state the type of deviation, and then you try to explain. State what is observed when a mixture of trichloromethane and chloroform, they are mixed. Explain your answers. So even if you don't explain this, but my interest now is in these two. Okay, first do this and then you do this. If you want any help, you can ask anything. I hope you can do. Yeah, guys, I've seen your work. By the way, for those who be watching this video and other coming videos, when we reach where I give work, you pause the video, you also do work. Now when you finish at your own pace, when you finish, then you start the video. You don't start, you continue from where I stopped from, because I usually stop recording and then I attend to these people as they are doing work, and then after they have done everything, and then I come and do correction. So when you are watching the video, always pause, okay, and then you do, and after you resume. So now we have trichloromethane, and trichloromethane is just CH3. Let me use this permanent ink. Let me use this. So trichloromethane is just CH3. No, it is CH and then Cl3. Trichloromethane. And what is the RFM? Why are we looking for the RFM? We want to determine the number of moles of trichloromethane and the number of moles of propanone that were used, so that we can determine the mole fraction. Okay? So it's what we are doing. So the RFM is going to be 12 plus 1 plus, what is the answer? 3 times 35.5. What is the answer? You hurry up. So that will be the answer. Then RFM of propanone, and propanone is CH3.
Shana, where I was going to make the mistake is on methane. I think methane is CH3.
No, this is trichloromethane, which is CH. It is methane, meaning it has one carbon atom, and trichloro, meaning it has 3 chloride atoms. The rest are hydrogens, and in this case it is just 1. So this one will be 12 times 3, 12 times 3, which is 36, I think, plus 3, 6 times 1, which is 6, plus 6, and then plus 12. So what is the answer here? Somebody with a calic? No one? Hmm.
118.5.
So this is 118.5. This is the RFM of trichloromethane. And then this one? It is
64.
64. Yes. So the RFM of propanone, 64, and the RFM of trichloromethane, 1. Now, after getting the RFM, then we shall use moles. We shall get moles of...
Teacher, it is 54, not 64.
Oh, it's okay. Sorry for that. Sorry. So it is 64. So 5, 4. So we shall get moles of trichloromethane used. Which is 11.95 grams, because we shall use these moles to get the mole fraction. Now, why are we doing all this, by the way? That should be the real question you should be asking. We want to determine, we are given the vapor pressure of this liquid mixture. Where is it? It's here. And this one was determined experimentally. Now, the question wants, how does the liquid mixture deviate from Raoult's law? Then we are going to use the Raoult's law, and remember the Raoult's law, the partial pressure, the total partial pressure of the liquid mixture is going to be the partial vapor pressure of one component, which is A, times its mole fraction in the liquid mixture, then plus the partial vapor pressure of another component B times its mole fraction in the liquid mixture. So from this, now to do this, we are trying to find the mole fractions of these two components in the liquid mixture. And so this will be 11 out of 118, I think, 0.5. Okay? And I think here it is 0.1. This is 0.1. Uh-huh. Somebody with a canic? 1 watt? Yeah, even if. Uh-huh.
There where we calculated the more amount of
Yes.
we got 12 times 3 plus 6 and 12 8 because of what, that of what is 16.
Which water?
That of oxygen on propanol.
Hey,
Oxygen it
you
is
put there. It's okay, I get you. Hey, this is 16. Yeah, sorry for that. Thanks for that correction. It was just, it's okay. So what do you get? So plus 4, this will be 58, eh? Moles of propanol. This is C. I hope we are all following. And then this is CH3. So we shall get what we used, which is 14.5 grams. You guys, you should be doing this calculation on the calculator out of 58. So what shall we get? Dash moles. Okay? Dash moles. Then we shall get the mole fraction. Okay? And the mole fraction of let's say trichloromethane. Let me call this one T and call this one P. So the mole fraction of trichloromethane is going to be what is is it 0.1? 0.1 something out of the total number of moles. You guys hurry up and get for me the answers. You guys hurry up and get for me the answers. This is 0.25, eh? So plus 0.25. Yes, 0.25. 0.25 plus 1. This is plus. Okay, let me, for clarity, let's delete this. This handwriting wasn't fair. So this will be 0.1 plus 0.25. So what's the answer? What is the answer here? And what is the answer here?
0.28.
So this is 0.28. And then what's the answer here?
0.75, 0.78.
0.7. Does it add to 1? 0.
0.28.
No, this is 28. This one is supposed to be 7.2. It should up to 1. If it was okay. Is it correct? Does it add to 1? If our calculation was correct, then it should add up to 1. Is it?
We are getting 1.5
You're getting 1.5. Where?
when we add those more fractions.
This is 2.
280. Yes, it adds.
This one adds to 1. But
Yes,
if you got this in this calculation, then this one must be 0.72. Not so?
yes, it is.
The reason you didn't add, yeah, I get. You probably didn't put the 5 here. Now from this, then we can get our partial pressure. Okay? And then we compare this partial pressure with the one predicted by the Raoult's law. Sorry, with the experimental one. So let's fix in. So our P therefore is going to be, okay? So P of trichloromethane, it is 380. So it will be 380 times 0.28. Then we add there 300 times 0.72. So what is the answer? What's the answer? It is
322.4.
322.4. Now, is this the same answer that you got?
No. Simple mistake.
Excuse me, teacher.
Yes.
The one for propanone, is 380.
We have exchanged. Eh,
Okay.
yeah, we have exchanged. I thought the way the question was said, it's the same way. Thanks for that observation. So let's do it again. So you put, and then yes. So the mole fraction of propanone, it is this 0.72, and the mole fraction of trichloromethane, it is 0.28. Yeah, thanks for that observation. It was really good, and it will save us from making a wrong conclusion. So what's the answer then? It is
380.4.
380.4, right? Yes. So if you've done this, then now this is what is predicted by Raoult's law. Now, if we compare what is predicted by Raoult's law and what is given experimentally, how are the two related? You see that the one that is gotten experimentally is less than what is predicted by the Raoult's law. So therefore, how does it deviate? How does it deviate? State the type of deviation. So for this part, this is how you are supposed to do it. The whole of this calculation that you've done, that's how you are supposed to do it. Then state the type of deviation. It is negative deviation, because you see, it is what we got from the experiment is less than what is predicted by the Raoult's law. So meaning this is a negative deviation. Explanation, that's what you give. What is predicted by the Raoult's law is actually higher than what is determined experimentally. You are explaining this answer. Not so? Yes. Maybe you can also go ahead and tell us that the adhesive forces of attraction, that is the intermolecular forces of attraction between unlike molecules, okay, are actually stronger than the intermolecular forces of attraction between like molecules. And so what does that imply? You're going to reduce the escaping tendency when the two are mixed. And if you reduce the escaping tendency, then the vapor pressure is going to reduce or to decrease. Hence, the solution mixture will behave negatively from Raoult's law, or will deviate negatively from Raoult's law. So it's basically as simple as that. So guys, I think next time we shall begin from maybe property. No, let's talk about properties, and then we know that next time we shall begin with positive deviation and steam distillation, and yeah, we proceed. So number one, their total volume decrease when the liquid mixtures or when the two components are mixed. Remember, with ideal there is no volume change, but here the total volume decreases. Why? Because the force of attraction formed are strong, so the individual molecules.
Excuse me, sir.
Yes.
Did you talk about the observation between propanol and trichloromethane?
No, I didn't talk about it because it wasn't part of our today's deviation. So the total volume is going to decrease when the two liquids are mixed. Why? Because the force of attraction between the new intermolecular force of attraction between unlike molecules are strong. So liquids, they will be strongly attracted to each other, which leads to a decrease in volume. The heat is going to be given off, okay? Because breaking a bond requires energy, and the formation of bond, energy is given out. So the energy that is used to break the bonds, to break the intermolecular forces of attraction between the like molecules, is little compared to the energy that is evolved when the new forces of attraction are formed between the unlike molecules. Hence, heat is going to be evolved. Then the adhesive forces of attraction between components are stronger than the cohesive forces, or the forces between the individual molecules, the molecules themselves. Okay? Yes. So basically, those are the three properties. Remember, in ideal solutions, no heat change, no volume change, and the forces, the adhesive and cohesive forces, are equal. But here there is a decrease and heat is given out. Why? Because the adhesive forces are stronger than the cohesive forces. So you can go and think about how the properties will vary as far as positive deviation is concerned. Otherwise, guys, yeah, thanks for attending to the today's lesson, and let's all subscribe. Subscribe to receive new updates. Thank you.